right. Well, let's go ahead and get into it. This is a topic that is talked about, but that's about it. People kind of mention its existence, but they don't really delve into the details. And that topic is going to be continuous mode safety functions or high demand mode safety functions. When you go into the standard, you note that, well, if I have a high demand mode or a continuous mode safety function, I need to achieve a certain frequency. And yet you go to all the usual suspects for doing SIL verification calculations, all the typical software vendors, Connexus included, and nobody has the high demand mode continuous mode calculations because it requires a complete paradigm shift in what you're doing. Also, what I'm going to show you is that in the chemical process industries, if you have a continuous mode safety function or a high demand mode, really high demand mode, continuous mode safety function, you should be redesigning your control, not trying to patch a control problem with a safety system. So the first and best approach to addressing continuous mode safety functions is redesign your basic process control so that it's not a continuous mode safety function. And then you could go back to calculating probabilities. But alas, if you're stuck and you do need to calculate an achievement of a performance target, it needs to be in terms of frequency. And not a whole lot of people are going to help you out with a piece of canned software, because another thing to note, I've been doing this safety instrumented system stuff for about 30 years. How many high demand mode, continuous mode safety functions have I designed? Two. So it's not something that you're going to run into all the time. And of those two, only one was actually really designed because I convinced the other person to redo their basic process control. So I'm going to be jumping around. Ultimately, we're going to land in our Arbor software for fault tree analysis, where we're going to do our actual calculation. But we're going to start off by actually giving you a scenario and picking a SIL target for that one thing. It's been anonymized to protect the guilty, but we're gonna go over it. As a matter of fact, it's a very famous example, because if you've taken the ISA EC52 class, it's one of the examples in the class. So let's go ahead and start there. I'm going to begin by sharing my screens. All right, so before I go into the actual example, this safety function is what we're going to be looking at. I have an oxygen analyzer, and if the oxygen is high, I need to close the inlet valves that are putting air into my batch oxidation reaction. So we'll come back to that. We will also come back to this table here, which defines what the safety integrity levels are for the continuous mode of operation. But we will begin with a little bit of a discussion of continuous mode SIL assignment. Okay, so what is continuous mode? Why does it change everything that we do about how we run our calculations? Well, there are some control functions. And I'm going to make that clear, because when you're in the continuous mode, you're actually trying to control using your safety instrumented system instead of your basic process control system. Now, there are some control functions that you can't make them safe. So the classic example, and that's why I have like a vintage 1970s cockpit here with all the flashing lights and switches, would be an airplane rudder. So the airplane rudder is the thing on the back that goes kind of back and forth. And that kind of helps you turn in the air, as opposed to the ailerons, which are on the wings, the rudders on the tail. So what is the safe failure position of an airplane rudder? Well, if the rudder fails all the way to the side, either side, you're going to go into a flat spin and crash immediately. If it fails in place, you're just basically not going to be able to turn, and you're going to crash eventually. So there is no safe state for a failure of an airplane rudder. It has to work. And ultimately, when that control fails, you have the consequence. So the first big realization about continuous mode is that failure of the safety instrumented function is the initiating event. It's the cause. And as a result, a lot of the probabilistic stuff that we would like to do doesn't make sense, because we would be violating all of our rare event approximations. Okay, so if control failure directly results in a consequence, whether it's immediately or an hour later or a week later, if failure of the control results in a consequence, you're effectively in a continuous mode or a high demand mode. So in the continuous mode again, the SIF failure is the initiating event. And as soon as you heard me say initiating event, those of you that are familiar with LOPA know that that means it has to be a frequency. It has to be a rate. It cannot be a probability of failure. Definitely not a probability of failure on demand. Now, don't get me started on probability of failure per hour. It's a rate. Please, people, it's a rate. It's a frequency. So now we have kind of our LOPA equation that we would typically use to determine performance targets. And ultimately, what you're doing for a continuous mode safety function during the SIL selection phase is you need to pick the frequency that is going to make risk tolerable. Well, what frequency is going to make risk tolerable? The target maximum event likelihood, or the target maximum frequency, whatever you call it in your organization. So for any particular level of consequence, there's a frequency at which that consequence is deemed to be tolerable. We just need to make sure that in our design of the scenario, we don't violate that frequency. So the allowable failure rate of the SIF is going to be equal to the target frequency divided by the probability of failure of any non-SIF IPL that might be present. And the thing about continuous mode is things are moving fast. So it's really hard to take credit for anything else. Basically, you need to make sure that your SIF failure rate is going to be equal to or less than your target maximum event likelihood most of the time. Okay, so that's kind of the theory behind it. When you determine what your frequency is, it's going to fall into a range. So let's say my frequency was 5 times 10 to the minus 6. That's going to fall into the SIL1 range. But similarly to when you calculate a risk reduction factor, you're going to use that number and not just the SIL range in general as your performance target. So you're going to end up sticking to your performance target. Okay, so let's talk a little bit about the scenario. And again, take the EC50 class if you haven't already. I will go into this in a lot more detail. But what we have in this example is a plant that I worked with on the south side of Chicago, southwest side of Chicago. They were doing a batch oxidation reaction. So inside that reactor vessel that you see there, it gets charged with some material, which is proprietary, but let's just say it is in the BTX, benzene, toluene, xylene family of chemicals, and I'll just leave it at that. What we're trying to do is we're trying to hook an oxygen molecule into this BTX component to make a more valuable product, which is actually, I think it's a plasticizer, is the end use of this chemical. So how do we do this? Well, we charge that reactor vessel with material. And then we put in a liquid catalyst and we mix it up. Then we're going to heat the material up to hot. I don't remember off the top of my head. Let's call it 300 to 500 degree Fahrenheit range. Once everything is ready to go, then we're going to turn on our air blower, and the air blower is going to blow air through a sparger into this batch reaction vessel, and it will react. All of the oxygen in the air coming in is going to react with the hydrocarbons. Now, if you go above the reactor vessel, you're going to follow some piping, which is going to take the waste gas, and it's going to go through an electrostatic precipitator, and it's going to go out to atmosphere. How EPA allowed this, I don't know. But ultimately, we're going to have spent air, which is going to be the air with the oxygen depleted out of it. Plus, you've got a BTX component that's really, really hot. So a lot of hydrocarbons are going to vaporize, and that's going to be in that mixture too. Now, we're going to send this mixture out to atmosphere through a bag house with an electrostatic precipitator, because we're making fine dust chemicals. So we want to catch any of the fine dust before it's released out to atmosphere. Now, the reason that I note this is those of you that are in the know will know that an electrostatic precipitator is a spectacular source of ignition. If you have a flammable mixture going through your ESP, it is going to ignite. And honestly, that's the problem here. Okay, so in this plant, they're going to do this batch oxidation reaction. They're going to do about 30 batches per week, which is going to be about 3 or 4 batches per day. Now, in terms of basic process control, or is it safety, or is it control, or is it both? What they do, the way they run this plant, is that at the end of the batch, they know that the batch is done because oxygen breaks through and it starts going into the overhead stream, which is going to be detected by one of those 2 oxygen analyzers in the overhead stream. And then once you detect that it breaks through, you're going to close the inlet valves and you're going to stop the air blower. Okay, that's your basic process control. So 30 times a week, we're relying on this SIS/control function to operate, because if it doesn't work, I am going to very quickly send a flammable mixture out to my ESP, and it's going to explode. Now, the good news. So, when you're in a situation like this, you got to get a little bit of levity, start cracking some jokes. And I said, when's the last time you blew this thing up? If you want to have fun at a chemical plant, ask when the last time they blew something up is, and you will always get a horrifying answer, I assure you. They said, we've been on a pretty good streak. It's been a couple years since we've blown it up. Ooh, okay. So that's bad. But the good thing is the electrostatic precipitator is on the roof of the building. So when this explosion happens, it blows the ESP up into a whole bunch of small pieces, but it's up on the roof and no one generally gets injuries of any kind. So it's all an equipment damage. So this all ended up being equipment protection. All right, so how do we pick a SIL target for this scenario? Well, we know that it's continuous mode because, well, I could do another long rehash of what it means to be continuous mode, but today's standard says if you challenge your safety function more than once a year, you're going to be in high demand mode / continuous mode. And we're challenging it 30 times 52 times a year. So a lot more frequently than that. It is solidly in the continuous mode of operation. Mathematically speaking, what we're really concerned with is tests of the safety instrumented function need to be frequent in comparison to challenges. That's the big driver here. A lot of what we do in SIS engineering is based on a series of rare event approximations, where if an event is sufficiently rare, we can do our math a particular way. But if it's not rare, our math falls apart. And that is the case here. So if let's say I was testing this safety function once every 2 years. So for once every 2-year test, I challenged it about 300 times. So when the SIS fails, are you going to find out because you tested it and it didn't work? Not bloody likely. You're going to find out about it because you challenged the safety function, it didn't operate, and I had my consequence. So the expectation is that you're never going to detect a failure with a test. You are always going to detect the failure by the consequence occurring. So if that is the case, there is no value in testing anymore. And if there's no value in testing, all of my probability of failure on demand math absolutely goes out the window. And the only thing that matters is how frequently will this device fail, because when it fails, I will have a consequence. And what we did is the TMEL tables that we used in the exercise said our target maximum event likelihood for a $2 million loss is 3 times 10 to the minus 3. That just came right out of the consequence category tables. Then we plug our information into that maximum allowable failure rate calculation. And basically the TMEL is 3 times 10 to the minus 3. The PFD of the non-SIF IPLs is, well, there are no non-SIF IPLs, so it's going to be a 1. There was an alarm, but we, in the exercise, it became apparent that there's not enough time for the operator to respond. So we're going to divide 3 times 10 to the minus 3 by 1, and we're still going to have 3 times 10 to the minus 3. Now, the real tricky part about this is that your TMELs are in years, and your failure rate range for your SIL targets is going to be in hours. So we ended up calculating that I need a SIF failure rate of 3.42 times 10 to the minus 7, which falls right into the meaty middle part of the SIL2 range. Now, this is our starting point, and now we're going to say, okay, if I wanted to design this, how do I verify that I achieve that frequency target? But before I get to that, what did we actually do for this plant? We had them change their basic process control. So instead of ending the batch when you get a high oxygen alarm, we totalized the flow of air going into the reactor, compared that against the weight of the reactor, and basically when the totalized flow of air has consumed 95% of the reaction or the reactants, we just stop the reaction. So we are not relying on that oxygen analyzer to be our control. We put in an actual real basic process control functionality, which pushed the high oxygen back into low demand mode, where you can use all your typical standard equations that you're used to. So let's go ahead and take a look at those typical standard equations. Once again, from that ISA, this is from the EC50, but when you look at the equations for calculating your achievement of a SIL, they are all in terms of PFD average. These equations aren't set up to show you a frequency. Could we set up equations to do frequencies? Certainly. I'll show you the fault trees, and if you want to solve the fault tree symbolically to come up with an equation, more power to you. I'm just going to go ahead and stick with the fault trees. Now, the important part of the equations that you're looking at here, even though they're for PFD, there are the components that we need to think about, and you're going to need to think about these components for a continuous mode calculation the same way you would for a demand mode calculation, where you're going to have different types of failures depending on what type of testing, if you will, is required to know that that failure exists, and then some other parameters. So let's go through them one at a time. The first one is always the most complicated one, and that's going to be the dangerous detected portion. So if I can detect that a failure is occurring, has occurred in my device, whether it's something like a watchdog timer on your safety PLC, or just built-in diagnostics on your transmitters, or partial stroke tests of a valve, which is really sketchy out of the gate, but it's even sketchier here because that test interval on a partial stroke test is so long that you definitely shouldn't take credit for it in something that is continuous mode. But diagnostics, if they occur fast in comparison to the amount of time that it takes, the process safety time, the amount of time that it takes to get into trouble, then you can probably take credit for them if you convert your dangerous detected failure into a spurious trip. So if you detect that the component has failed, you just trigger a shutdown function, and then you'll be able to take credit for that lambda DD by actually converting it into a lambda S. If all you do is put up an alarm saying my component is in the failed state. So if you're using comparison diagnostics, I've got a deviation alarm between my SIS transmitter and my BPCS transmitter. And you're relying on someone going out to the field and repairing whichever one of those two devices has failed, you don't have enough time. Well, you probably don't have enough time. In this case, a batch is only going to require like a couple hours. So the danger is going to happen before your repair will occur. So you need to look at that mean repair time. You need to look at the automatic diagnostic test interval to make sure that you could do something about it before the plant goes to hell at the end of the day. All right. So there's the DD portion. The DU portion is pretty straightforward. That's the dangerous failures that are not detected by automatic diagnostics. Got one really good piece of news for you. Never detected doesn't matter because testing doesn't matter. So a proof test on a continuous mode safety function provides no benefit. Are you going to do it anyway just to make yourself feel better? Maybe do it at the turnaround? Sure. But you can't take any credit for it mathematically because the test is not frequent enough to provide any modicum of risk reduction. So if we're not taking any credit for testing, the quality of the test doesn't matter because we're not taking credit for it in the first place. So we're going to ignore the never detected portion because it's all undetected. All undetected failures are going to be treated the same way, which is as soon as the function is challenged, you're going to have the consequence, whether it would have been detected by a proof test or not. Bypassing. Bypassing is really tricky because you're using the loop for control. So you'd have to basically put the loop in the bypass and manually control it. I don't like the sound of that. Online testing of components, well, once again, testing is superfluous. As soon as the device fails, we're going to get a consequence. So the bypass for online testing goes out the window. And then common cause, we're always going to address common cause, and I'll show you how common cause gets addressed when we get into the fault tree. So ultimately, the terms that you're going to need to think about are going to be the dangerous detected and dangerous undetected. And you'll never need to calculate the frequency of a dangerous detected failure as part of your let me step back on that. The treatment of the dangerous detected portion depends on if you are automatically shutting down or not. If you are not automatically shutting down on a dangerous detected failure, it effectively is not detected. You're not going to be able to repair out, so just add the DD back to the DU, and that's the number that you're going to use in your calculation. All right, so addressing all these terms, at the end of the day, we're basically going to be looking at one term, and that's going to be the DU. If a DU failure happens, we have our consequence unless we have some redundancy. Now, if we have some redundancy, excuse me, we may be able to play some other games. What we just did is we picked a SIL target, and we have a safety function that is oxygen analyzer, safety PLC, and final element subsystem, which is actually 1 out of 2 voting. Now, if you look at your fault tolerance tables, to get the SIL2 in continuous mode, you need 1 degree of fault tolerance for everything. So you would have needed to put fault tolerance on that oxygen analyzer too, which is a very expensive proposition. But I digress. Let me maximize my screen here. I'm going to log into the Connexus Integrated Safety Suite. I am just going to go into my playground sandbox folder here, and I'm just going to create a new study. So I'm going to create a new Arbor study. Those of you who are in the know that this is our fault tree analysis tool. I'm going to call this continuous mode example, and I'm going to put number 7 in there. So next time I teach the EC52 training class, I will get to show people what a SIL verification for continuous mode looks like. And I'm going to create that. So now I'm in my fault tree analysis. Let me scooch Chris out of the way. And this is what our fault tree analysis tool looks like. And let's just go ahead and build things out. So I'm going to start at the top gate by giving it a description. And I am going to say high oxygen safety instrumented function fails. And I will clarify a little bit. Rate for continuous mode. All right, and let me hit update. So there is our top gate. Now, why is the safety instrumented function going to fail? This is exactly the same as everything else you've ever done. So I'm going to go into add gate mode, and I'm going to drop 3 gates underneath the top gate. And those 3 gates are going to be, let me switch back to edit mode, sensor sub system fails. And this is going to be logic solver sub system fails. And this is going to be final element subsystem fails. Okay. Now, the top gate, then now we can assign it some logic. So by default, everything is a transfer gate. Here we're going to do an OR. Okay, so that means that the SIF as a whole will fail if the sensor subsystem fails, or the logic solver subsystem fails, or the final element subsystem fails. Okay, this all should be very familiar because nothing here is really different from what you would have done for a low demand mode safety function. But now let's drill down into the details. And in the details, I am going to work on the final element subsystem because it has some redundancy, and that redundancy is going to make things interesting. So now the final element subsystem is going to fail when a couple things happen. So I'm going to start out by putting another gate here, going into edit mode, and then I am going to put an event here, and then I'm going to put 2 events under gate 4. So let's kind of focus on this. All right, so why did I do what I just did? When you have a redundant subsystem, there is simultaneous independent failures and there are common cause failures. So for, oh, sorry about that. Let me go back into edit mode and delete this guy. I don't want him. So let's give this gate a name. Actually, before we give this gate a name, let's correct the logic under gate 3. So because the final element subsystem will fail if either I get simultaneous independent failures of the valves or a common cause failure of both valves, this is going to be an OR gate. Now, for gate number 4, I'm going to say simultaneous independent of the shut off valves. Okay, and this one is going to be an AND gate because it's a 1 out of 2 voting arrangement. So in a 1 out of 2 voting arrangement, the A valve has to fail and the B valve has to fail. And I'm going to hit update. And here we go. Now, as you look at this structure, let me kind of make it small, and then I'll make it bigger again in just a second. As you look at this structure, you're probably telling yourself, this is no different than what I would have done for a demand mode safety function. And you know what? You're right. But what is going to change is what we're going to do next when we start putting the fundamental models down. So let me begin. Actually, let me just do one of the valves. So if I go in, event number 2 is going to be valve A fails. Okay. Let me flesh out a couple of other things in the fault tree tool. So right underneath the description, you have a checkbox for initiating event. You have a checkbox for enabling event. If you know that one of the valves is always the cause, you could call it an initiating event and it will only evaluate the frequency. When you put the checkbox on initiating event, at the end of the day, we know that we're only evaluating frequency. For an enabling event, it never starts the chain of events. It only contributes to it. So if you think about LOPA, your initiating event is an initiator, but failure of your protection layers are all enablers. So enablers only have probabilities, they don't have frequencies. Whereas initiators only have frequencies, they don't have probabilities. Well, guess what? In this particular case, we're not going to check either one of those because we need both devices to serve both purposes. And which one of these two valves is the enabler versus which one is the initiator depends on who failed first. Whichever valve failed first is the enabler, and then the other valve is the initiator. And under the hood, all this math is being done. And I'll kind of, I might actually get a whiteboard out and kind of work through what's going on, because for some of you, knowing that there is frequencies under an AND gate is going to make your head explode, because you can't multiply frequencies together. Absolutely, I know you can't multiply frequencies together. I mean, we have software that does this. So I'll show you what the software is doing under the hood, which is not completely intuitive. So we'll come back to that in just a second. So all these events are going to be initiators and enablers. So we're not going to check either of those boxes. The next item down is the event model. So if something is always true or always false, please say right here that it's always true or always false, and it's going to make the math monumentally easier, because we can do all kinds of cut set simplification if we know it's a house event, and that's the terminology in fault tree analysis for something that's either always true or always false. But in this case, we are going to use the event model, and then we are going to create our event model. So what I'm going to do is I'm going to add a model from our library. So add new from library, the Connexa standard library, and I'm going to go into our final element database, and I am going to just do a generic air actuated ball valve. Okay, and for now, just to make the rest of the exercise simple, I'm going to ignore the fact that there's a solenoid there. I'm just going to deal with the valve itself and pretend that that's the only thing going on, just to make the view of the fault tree a little bit easier to understand what's going on. Now, in our analysis, what failure rate are we concerned about? Because in our database, we've got safe undetected, safe detected, dangerous undetected, dangerous detected failures. Well, I know that there are no dangerous detected failures, but I'm going to check it anyway, just to tell you that when you're putting in your failure rates, you're going to want to include the lambda DU failures. And if your detected failures are not resulting in a shutdown, you're going to want to include them here. If they are causing a shutdown, you don't include them here, but you include them, you add the lambda DD to lambda S when you're doing your spurious trip rate calculation. All right, so I'm just going to add both of them, even though there are no diagnostics, so lambda DD is 0, and we're going to end up with the same number. So now I'm going to hit insert, and I've shoved the failure rate out of our library. So 1.8 E minus 6 is air actuated ball valve generic lambda DU plus lambda DD. Now, the next thing that we're going to do is you automatically got a title and a description, but we need, and also the failure rate, but now we need to say, is this constant, is this overt, or is this covert? And this is where the changes happen. Constant is something that I'm not going to dwell on, because basically, if you know what the failure rate is, you just put it in as constant. If you know what the unavailability is or the probability is, you put it in as constant. You're going to use overt and covert when you want to calculate the frequency or calculate the unavailability of the system. Now, overt and covert, in the EC50 class, which if you haven't taken the EC50 class, come on, man, it's the best. You learn about failure modes, and you learn that in the demand mode of operation, when a safety instrument function fails dangerously, it is covert. It is hidden. You don't know about it until you perform the test. So the failure hides. But in the continuous mode of operation, the failure's not gonna hide, because when the failure happens, you're going to have a consequence. So we need to be dealing with frequencies. And instead of using the covert, which we would use if we were doing a demand mode calculation, we are going to use overt, or in some cases, you could just put in the failure rate using the constant model. I'll show you how that works when we go into the common cause factors. So for common cause factors, you could go either way. So basically, we're using overt because we're going to look at an unavailability, and nothing's going to be able to hide, because the failure of this safety function is what caused our demand. It's what's going to cause the consequence. So when you're in the overt model, you're going to put in your failure rate, you're going to put in your mean time to repair, you're going to put in a mission time. I'm going to go ahead and put in a 1-year mission time. Mission time doesn't come into the calculation unless it's extremely short or extremely long. And I'm going to need to do an entire webinar on how mission time is used. So mission time is not the test interval. Well, here I'm actually going to use the test interval, but it means something completely different that kind of makes sense, like in aeronautics, where you're going to launch a rocket, and from the rocket getting from point A to point B is a mission. The concept of a mission doesn't really exist in the process industries. So we'll generally put in our periodic test interval, but we don't need to test because it's a continuous mode safety function. Nevertheless, I could put in a wide variety of numbers in for mission time. Unless it's extremely low or extremely high, it's not going to factor into the calculations. The key here is we know what the failure rate is, and we have a mean repair time because we have redundancy. So if at the end of the batch, one valve closed, but the other valve didn't, we're going to be able to repair one of those valves before we start the next batch. So that's kind of a little bit of help. So I'm going to hit the update button here and hit update. So I've got a failure rate of 1E minus 1.80 minus 6 mean time to repair of 72 hours. Now, when I go to the other valve, I'm going to call it valve B fails. And I'm going to basically do the same thing. I'm going to just pick that same model since it's already built out. And there we go. So now let me try to run this. I don't know if it'll run or not. I've got a lot of empty data, but yeah, it will. So now what we were able to calculate is ignore the Q, because the probability doesn't mean anything. And what we're really concerned with is this frequency right here. So the frequency that both of those valves will fail at the same time, but independent of each other. That means one valve fails at one point in time due to one stress. The other valve fails at a different point in time due to a different stress. The frequency of that is 4.66 E minus 10. Now, under the hood, how did things get calculated? I am glad you asked. You saw a frequency under an AND gate, but you don't just multiply the frequencies together, because that doesn't make any sense. What you're basically doing there is you're saying, these two events need to happen at exactly the same point in time due to independent reasons. It makes my head hurt even thinking about it. What are you actually doing? You have an OR gate with two AND gates under it. So when the Arbor software sees this, the math that it actually performs looks like this. And if I have an A valve and a B valve, what's actually happening is, what is the frequency at which A fails while B is already in the failed state? And then what is the frequency that B fails while A is already in the failed state? So one of the valves fails first, it stays in the failed state and it's not repaired in time, and then the second failure occurs. So this is the structure on the right-hand side is what the software is actually doing. It's the frequency of A multiplied by probability of B being in the failed state, and then frequency of B multiplied by the probability of A being in the failed state. Add those things together. That's what allows you to get a frequency, even though it looked like I multiplied two frequencies together, but I did not. So hopefully that clarifies a little bit about why it looks like we're multiplying frequencies under an AND gate, but that's not what's happening under the hood when we do our minimal cut set resolution. All right, so that was the simultaneous independent failures. What do we do with common cause? Well, with common cause, it's just going to be a frequency. So the frequency, I'm going to go into an event model. I'm just going to add a new event model and call this valve common cause. Common cause. The type, I'm going to go ahead and leave it as constant because there's no redundancy here. So the frequency is what the frequency is. And the failure rate, what is the common cause failure rate? Well, the dangerous failure rate is 1.8 E minus 6. I'm going to go ahead and just use a common 10% beta factor, which is going to make that failure rate 1.8 E minus 7. I'll put 1.8 E minus 7 in here just to prevent the software from complaining that I left the field empty, but the number's not going to be used for anything. So I'm going to hit insert. And here I can call this an initiating event because when a common cause failure of the valves happens, the system as a whole failed and your consequence is going to occur. So let's call this a valve common cause failure, and I hit update. And now you'll see the numbers that I put in. When I rerun the calculation, you'll see, because I called it an initiator only for event 1 on the right side, it only calculated a frequency. And guess what? Those of you that have taken EC50 and EC54 with me know that whenever you have a redundant arrangement, common cause usually is going to dominate the overall equation. And guess what? 1.8 E minus 7 out of 1.8 E minus 7 all came from common cause failures. So no big surprise there. But ultimately, this is how things happen. So if I wanted to flesh out the rest of the exercise, I would put in a 1 out of 1 for my logic solver. I would put a 1 out of 1 for my sensor. And again, the key is when you're running your models, you're not running the covert model, you're running the overt model, which is going to generate a frequency for you. And that frequency is going to translate into this top event. So without even looking at the rest of the safety instrumented function, I've already got a frequency of 1.8 E minus 7. The failure rate out of the exercise was 3 point, let's call it, it was like 3 E minus 6. 3 E minus 6 or 3 E minus 7 is the failure rate that we were looking for. Basically, what you're going to see is without the benefit of the periodic proof test to reset your probability of failure to 0, without the benefit of that testing, it's real hard to achieve SIL targets in the continuous mode of operation. All you have is that failure rate and some redundancy to fall back on. You don't have that periodic proof test. So getting into SIL 2 even without doing a lot of redundancy all along the way is probably not even going to be possible. But with that, that kind of is my spiel for today. So kind of going back to the beginning of the lecture, continuous mode is basically someone didn't design your chemical plant right, and you're using a safety function as a controller. And as a result, when that loop fails or very shortly thereafter, the consequence will occur. And we expect the consequence to occur before the next proof test. As a result, proof testing is meaningless. We can't take any credit for it, and we need to run our calculations in the frequency domain. When we run our frequency calculations in the frequency domain, the fault tree structure will look similar to what you would see if you were doing a PFD calculation, but instead of using the covert mode and looking at the probability, you're going to use the overt mode and look at the frequencies, because the frequencies are all that matter at the end of the day. So with that, let me go ahead and step into Q&A mode.
Yeah, so question. So it seems like we're mostly focused on continuous mode, which is just if a SIF, fails during operation, you're instantly going to fail. There's also the high demand, which is just, okay, it's more than once per year. There's no parsing between those two. If we basically just treat high demand as continuous mode, is that correct? Or is there any other delineations or differences on how we approach the design of a high demand mode SIF versus a continuous mode SIF?
Yeah, mathematically speaking, you will treat them the same way for DU failures. The only thing that gets a little bit interesting and confusing is diagnostics. Now, in my example, when the safety function fails, you're going to have a consequence within a couple hours. But let's say I'm challenging my safety function once every 6 months. Now, if I have a dangerous detected failure, I have the ability to do some repair. So if my challenges are once every 6 months and my repair time is 72 hours, now I can make a greater case for being able to take credit for diagnostics, even if the diagnostics don't result in a shutdown, because now I have time to perform that 72-hour repair, likely before the next time a challenge arrives. So
that makes sense.
That math can get a little bit interesting. But even with a high demand mode, and let's let's talk a little bit about kind of what happened in the standards committee meetings when they made the simplification, because the 2003 version of the 61511 standard said you're in a high demand mode if your challenges are frequent in comparison to testing. In 2016, we just said 1 year. And the reason is so many people just couldn't mentally grasp the relationship between challenge frequency and testing frequency, that we just said, you know what, let's just say that, well, a typical plant will test once a year. So if you're challenging more than that, that's probably too much.
Mhm.
And that's where that delineation came from. So what we're also expecting is that if you're challenging more than once a year, the expectation is that you're going to identify a failure not by a test, but by a demand on the process that results in a consequence. And whether that's 6 months or 2 hours, that's the assumption, is that a test isn't going to help tell us anything. When we get a failure, we're going to know because the plant blew up.
Yep. Okay.
Yep. Excellent.
Thanks.
Uh-huh. Thanks, everyone.